Welcome to another lecture. In this lecture, we will be looking at chapter 2, and we'll be looking at atoms, which are the basic composition of matter. Remember again that matter is anything that occupies space and has mass. So let us start our study. Atoms. So let's first of all define atoms. Atoms are the basic unit of matter. Basic unit. It comes from the Greek word indivisible. As you'll see in your text, it was once thought to be the smallest things that exist in the universe. So atoms again are the basic unit of matter. Let's introduce another term here, and that is element. An element is a substance or matter that consists of identical atoms. Notice identical atoms. So if you have an element, it consists of particles that are very small, that's called atoms, and they are all identical. So just think about that for a second. An element is matter that consists of identical atoms. And once again, atoms are essentially the smallest component of matter. Example, carbon is an element, and all of the atoms of carbon are the same. Same for hydrogen. We're very familiar with hydrogen and iron. So there are 118 known elements. Okay, so you can see matter, we are now defining the basic component of matter, breaking it down. There are 98 natural occurring, and the others have been made in the lab. The symbols are typically 1 or 2 letters. What's meant by symbols? Symbols here is instead of using the entire word, a lot of times in chemistry we'll use symbols to represent these elements. And the names are typically derived from various places or people or as we've seen here, from planets. So the basic take-home lesson from this slide is a definition of atom, smallest component. The definition of element. Element consists of identical atoms. In this table here, it shows the periodic table that you're familiar with, or we've seen quite a bit. So this is the periodic table of elements. So these are all the elements that exist in the universe. As you've seen in the previous slide, it's 118. So they're all here on the periodic table. One thing I should point out here is the symbols. So notice carbon is C. I don't expect you to memorize the periodic table and the symbols, but I expect you to have the periodic table available. It's your tool. It's what you'll use to solve problems. So make sure you have your periodic table available every time you study your chemistry. Let us go on. Let's introduce another term here, compound. So let's define it. Make sure we understand it, because we're going to ask you, what is a compound? Or examples of compounds later on. A compound is a pure matter that is made up of two or more elements. Keyword here, fixed ratio. So let's think that through. A compound is a pure substance or matter that's made up of two or more elements in a fixed ratio. Remember, the elements are the substances or the matter that are shown on the periodic table. So a compound consists of the elements of the periodic table in a fixed ratio. The formula of a compound, we're always representing compounds different ways. So the formula of a compound tells us the ratio. For example, NaCl. If you look at your periodic table, you'll see that Na here means sodium and Cl here is the symbol for chlorine. So the way that's written is NaCl. The fixed ratio is 1 sodium to 1 chlorine, as we have seen here, 1 to 1. Another example is water. Notice it's written a little differently here because it has a subscript 2. This tells us the ratio of hydrogen atoms to oxygen atoms, which means that there's 2 hydrogens to 1 oxygen, so we write it as H2O. Notice we do not write it as H2O1 because 1 is understood. Let's go on. This represents here the symbols or the way we represent molecules in chemistry. This is the molecular formula, as we have discussed before. This is the structural formula. We'll use this a lot later on in the course, and this one we'll use later on in the course when we start looking at reactions. But for the time being, for right now, this is what we are most interested in, and you should focus on is the molecular formula. Okay? So just to make sure that we understand what we just discussed, let us try to answer this question. Aluminum and fluorine form a compound. Notice a compound here in which aluminum and fluorine has a fixed ratio of 1 to 3. 1 to 3, fixed ratio for a compound. So the question now is, what is the molecular formula of that compound that has aluminum and fluorine in a fixed ratio of 1 to 3? So what you'll need to do is to get your periodic table and see if you can find aluminum and see if you can find fluorine. Once you find aluminum, you'll discover that the symbol is Al. Once you find fluorine, you'll discover that the symbol is F. So this choice here has a problem because A is not one of the symbols for the elements. AlFl3, we have a problem here because Fl is not the symbol for fluorine. So look out for this carefully because we want to make sure that you understand the concepts and we want to make sure that you can apply the concepts. Let's look at this one. Al is the symbol for aluminum. F is the symbol for fluorine. The next question is that in the ratio that's given? Remember that there is a 1 here that's typically not written in. So this ratio here is AL1 F3. Looks like it could be it. The next possible choice is ALF2 times 3, which means 6, which is not the ratio here. So let's see what's the answer on the next slide. You can tell that this is the correct answer because it fits the 1 to 3 ratio and the symbols for aluminum and fluorine matches up. So you should be able to look at any compound and determine that fixed ratio based on the symbol of the elements. Let's look at the next slide here, and this is another concept that we're introducing here, and this is of a mixture. So let's again, as usual, define a mixture, and then we'll give you some examples to have you apply that definition. A mixture is a combination of 2 or more pure substances. Same as before. But notice here, there's a criterion here that's different. It may be present in any ratio. Notice it's not fixed, any ratio. And each substance has different physical properties. But the main thing is right here. The ratio is not fixed. Examples. A mixture of sodium chloride, salt, and water is a mixture. Or, let's state it differently, a combination of sodium chloride and water is a mixture. A combination of oil and water is a mixture. Notice again, the ratio does not have to be fixed. If you take 10 grams of salt and 6 mils of water and mix it up, you do have a mixture, not a compound. A mixture because the ratio is not fixed. Let us apply that definition here or define it further. We have a homogeneous mixture. A homogeneous mixture is one that is uniform throughout, identical wherever you look. So if you have a mixture and you look at that mixture, if the composition of that mixture is uniform throughout, the same throughout, it is described as a homogeneous mixture. Another term is heterogeneous mixture. A heterogeneous mixture, as you can see here, has non-uniform mixture throughout. So on inspection of a heterogeneous mixture, you will see a difference in composition. You will see a difference in composition. So at this point, you should be thinking of, if I should have a mixture of salt and water, is that a homogeneous mixture or is that a heterogeneous mixture? So you have to really visualize that mixture and apply these definitions here. Let us look at the next slide, which has some examples. So, if you have a cup of soup, is that a mixture, first of all? Yes, it is, because, of course, as you know, the ratio of the components is not fixed. So, next, is it a homogeneous mixture or is it a heterogeneous mixture? Looking at this, you can see here the noodles and you can see here a liquid. So therefore that is a heterogeneous mixture. The next example here is blood, especially for the students who are in the medical field. You will see that quite a bit. So looking at blood, that's a tricky one, because looking at it, it appears as if it's uniform throughout, just looking at it with a naked eye. However, if you should put it under a microscope, what you will see are these different components, platelets. So the question now is it a homogeneous mixture or is it a heterogeneous mixture? Looking at it with the naked eye, it would appear that it's a homogeneous mixture. But if you have a microscope, it does not appear to be a homogeneous mixture. So the conclusion is it's a heterogeneous mixture based on the instrument that we have to look at it. And we do have microscopes available in today's technology, so we'll define blood as a heterogeneous mixture. Let us look at the last example here, a mixture of sodium chloride and water, salt and water. Looking at it, you can see that it's a uniform throughout. If you put it under a microscope, you will still see a uniform composition throughout. We will see later on, however, that it's made up of molecules, but we cannot see those molecules based on a microscope. So based on our definition, this is now a homogeneous mixture. So again, what you need to do at this point is to look around your environment and determine if what you see is a homogeneous mixture or a heterogeneous mixture. Let us look at this example here. If we know the properties of the individual components of a mixture, it can be separated. So mixture, if we know the properties of the components, we can separate it. Notice, for a compound, this cannot be done because it has a fixed ratio and it's held together and cannot be separated. But for a mixture, they can be separated. An example here is iron and sulfur. We know that iron has magnetic properties. So that's a physical property of iron. Sulfur does not have magnetic properties. So if you have a mixture here of iron and sulfur, you can separate that because you can now use a magnet to attract the iron, and what's left behind is the sulfur. So again, mixtures can be separated by physical means. Compounds cannot. Here is a question, just to make sure we understand the concept of mixtures. Which of the following statements describe a mixture? Notice again, I'm underlining the key aspects of my question so that I fully understand what's being asked, so that when I look at the possibilities here, I can apply that understanding. So let's look at the first choice here. A mixture does not, look out for these words, not contain a fixed ratio by mass of components. Keyword not, fixed ratio. Need to think about that for a second. Let's look at the next choice. Chemical techniques are required to separate components of a mixture. Remember, if it's a mixture, it's a physical technique that's required for separation, not a chemical technique. And of course here both A and B are correct or neither A or B. So think about that for a second. You may want to pause the video and think it through for a second, because the answer is on the next slide. And so let's see what it is. So no surprise, a mixture does not contain fixed duration. And of course, as we know, chemical techniques are not required for that separation. Okay, so this is a summary of what we just discussed here. So we have matter, just about anything that occupies space and has a mass. So look around your environment, you will see matter. That can be classified as a pure substance, a pure matter, or a mixture. If it's a pure substance, it has a fixed composition. Pure substances are made up of elements, that's shown on the periodic table, and elements combine to form compounds, which we'll discuss. On the other hand, you could have a matter that's a mixture. And a mixture can be homogeneous, uniform composition, or heterogeneous, non-uniform composition. So you should be able to look around your environment, or when you go to the chemistry lab, look at that environment, and any matter that you see, you should be able to classify it as one of these. Okay, let's turn our attention now to the atom. So remember again, the atom is the basic unit of elements. Basic unit of elements. So way back in 17, well, this is his, the lifespan. So within that lifespan, John Dalton proposed his atomic theory. What he stated is that all matter is composed of very tiny particles called atoms. All matter composed of very tiny particles called atoms. And just to repeat, all atoms of the same element have the same properties. In other words, the element carbon, all the atoms of carbon are the same. If you should look at another element such as nitrogen, all the atoms of that element nitrogen are the same, but they are different from the atoms of carbon. Let's introduce another term here, compounds. Compounds are formed from the chemical combination of two or more of the same or different kinds of atoms. So again, we've seen that definition before, the fixed ratio of the different elements. But now we're looking at it from the atomic level. Examples: sodium chloride is a compound because we have one sodium atom and one chlorine atom. Aluminum trichloride is a compound, one aluminum atom and three chlorine atoms. Same for sodium hydroxide. Molecules, another new term for us, are tightly held together, are atoms that are tightly held together by a unit called bonds, which we'll discuss later on. But for right now, the examples are water. You can see here it's composed of hydrogen and oxygen. And of course, nitrogen is tightly held together by bonds, but the atoms that are here are two nitrogen atoms. What you'll see here, for the time being, compounds and molecules are the same. We'll make a subtle distinction distinction later on in our discussion, but for the time being, a molecule and a compound, we'll say they're synonymous. Evidence of Dalton's theory. So again, a law that we look at here is a law of conservation of mass. Mass can neither be created or destroyed. So, if you have a reaction, here we got carbon monoxide, which consists of carbon atom and oxygen atom. You react this with lead oxide, which is lead Pb and oxygen. If there's a reaction, you get a product here as carbon monoxide and lead. The bottom line here is that we have over here carbon, oxygen, lead, and oxygen atoms. And over here we still have carbon, oxygen, and lead atoms. So we have not lost any of the atoms, and we have not gained any new atoms in the product. That's why it's called the law of conservation of mass, because we have not created any new atoms and we have not destroyed any new atoms in going from reactants here to our products. Okay, let's look at some more definitions. Monoatomic. By the way, this is monoatomic elements. Consist of single atoms. Single atoms. For example, helium consists of all the atoms that are the same. Neon consists of all the atoms that are the same. There's some elements that are diatomic. And the examples here are hydrogen. So you look at the periodic table, you see hydrogen, but in the real world it exists as H2. So you will not find in nature H, just H1. Same for nitrogen, nitrogen gas, oxygen, and some other examples here. So in nature they exist as diatomic. There are other possibilities. We have here ozone. So if you go and you collect ozone in nature, it exists as 3 atoms of oxygen, triatomic. Same for phosphorus, and sulfur exists as 8. An example of how this is shown here, represented here. So you can see H2, 2 atoms here, N2, 2 atoms again, O2, 2 atoms, and of course O3 has 3 atoms. Look at sulfur. Sulfur has 8 atoms that exist in nature. So if you should get a bottle of sulfur, there are basically 8 atoms that are bonded together, and not just sulfur by itself. Okay, let's turn our attention and look now at the structure of atoms. Now we're going to look really at what is an atom. What does it consist of? So let us look at this. The atoms consist here of protons, electrons, and neutrons. So we'll keep it simple and we'll just use these 3 particles to represent the atom. Notice the charge. The proton is +1, so it has a +1 charge. The electron, as you might imagine, has a -1 charge. The neutron has a 0 charge. It's not charged. So that is why the elements are neutral, because it consists of protons, which are positive charge, and electrons with a negative charge, and they cancel out each other. So you can assume at this point that an atom will have the same number of protons as electrons, because the atoms are neutral. They're not charged. Another thing I want to point out here on this table is the mass. Notice that it's extremely light. this is, the proton weighs 1.6726 times 10 to the negative 24. Negative 24 grams. As you can see, that's extremely light. Look at the electron, even lighter, 10 to the negative 28. As we said earlier, these numbers are so small, they are extremely difficult to write. So what is done in chemistry is we will use another representation. And we'll say 1 atomic mass unit is defined as this number in terms of mass. So what we'll see from here on now is not the mass in terms of grams, but we'll see the mass in terms of AMUs, atomic mass unit. Okay, let us continue and look at the structure of the atom. So, the structure of the atom looks like this. It's represented here. So imagine a sphere, such as a ball. So in the center of that sphere is the nucleus, which has the protons and neutrons. Key here is the nucleus has the protons and neutrons. Don't forget that. Outside the nucleus, as shown here, are the electrons. Outside the nucleus are the electrons. Don't forget that, because we'll use that concept whenever we start looking at reactions. And of course, this represents the size of the atom. As you can see here, it's pretty small, 10 to the negative 10 meters. So the bottom line is, just imagine the atom to be a sphere, like a ball, a tennis ball, or a basketball, but it's extremely small, much smaller than those balls. And in the center is another sphere which has the nucleus, which contains the protons and neutrons, and outside are the electrons. So here's the periodic table, and of course of the elements, and of course for each element here we have atoms. They are made up of atoms. So carbon, for example, is made up of atoms of carbon. The difference between carbon and nitrogen, for example, is the number of electrons and protons and neutrons are different in nitrogen than they are in carbon. The number are different. Okay, so let us look closer at the atomic structure. Let's introduce a couple more terms here. The mass number. Okay, so the mass number is the sum or the addition of the protons and neutrons. We know what those are. Those are the positive and the zero charge that are in the nucleus of the atom. Notice for this lecture we are introducing a lot of new terms. So your job here is to make sure you understand the concept of these terms, because as chemists we will communicate using these terms. So your first job is to make sure you understand. So let's repeat. So the mass number here, we'll use this term a lot, is the sum of the protons and neutrons. The atomic number is the number of protons. So in other words, instead of saying that this atom has 6 protons, we will say the atomic number of this atom is 6. So again, Make sure you understand these numbers because that is how we will communicate. Make sure you understand these terms, I should say, because this is how we will communicate. So looking at the periodic table, what you'll see is something like this, where carbon is the symbol, because we will not, from here on, we'll use symbols. Because you have your periodic table, so you can refer to your periodic table to see what C means. C here means carbon. You'll see a subscript. That's a larger number. And that is the mass number. Don't forget the mass number is defined here. You'll see a subscript to the left of that number, and that's the atomic number. And the atomic number is defined here, which is the number of protons. Again, another representation is we will write carbon as C or as carbon 12, or sometimes just C-12, because this 12 here represents the mass number. Isotopes. Let's look at another term, new term for us. Isotopes are atoms with the same number of protons but different number of neutrons. So just imagine again, an atom has the same number of protons as another one, but the only difference is it has more or less neutrons. Based on that difference, it's such a subtle difference that it's not another different atom, but it's now called an isotope. So, for example, carbon 12 has 6 protons and 6 neutrons. Carbon 13 has the same 6 protons and of course 6 electrons, but now it has 7 neutrons. And here's another isotope of carbon. Carbon 14 has the same 6 protons and of course 6 electrons, but now 8 neutrons. Of course, you will recall, or we will see later on, that carbon 12, this isotope, is used in carbon dating. So that's one practical application of isotopes. But let us look at what's found in nature. So if you went outside and you found some chlorine, for example, which is the elemental chlorine, what you will discover is that it consists of 2 isotopes, chlorine 35 and chlorine 37. So think about that for a second. These 2 chlorine atoms are essentially the same. They have the same number of protons and electrons. The only difference between chlorine 35 and chlorine 37, or these 2 isotopes, is the number of neutrons. One has 18, the other has 20. But we will just define them or look at them as chlorine 35 or chlorine 37 as 2 different isotopes. In nature, they exist in this composition. You will find them in this mixture. 75.77% is chlorine 35 and 24.23% will be chlorine 37. So once again, so we're not confused here. If you went outside and got a bottle of chlorine, it's a mixture of 2 isotopes. Mixture of 2 isotopes. Keyword here is mixture. It's constant. because wherever you go in the universe, this percentage will be the same. Let us see the relevance to the periodic table. So, because the periodic table shows the percent of this mixture, or the composition of this mixture of isotopes, what is done here is we have chlorine which has a 75.77% chlorine 35. Its weight is 34.97 AMUs. Notice again, it's AMUs, not in grams, so it's atomic mass unit. So that's the weight that has to be given. So that's weighed in the lab. You can imagine a very precise, accurate balance. Not really a balance, but it's estimated based on other experiments. And for the other chlorine, which is chlorine 37, the other isotope, it weighs 36.97 AMUs, and here is its natural abundance given. If you do this math here, notice it's the sum, so we got to add them up. You get this number, and this is the number that appears on the periodic table, because it is the atomic weight of chlorine. So let me see if I can break it down again. So if you went outside and got a bottle of chlorine, it is a mixture of two isotopes, chlorine 35 and chlorine 37. Because this mixture is constant, called the natural abundance, naturally occurring, we can determine the mass of one of these isotopes, which is 34.97, and the mass of the other isotope, which is 36.97. Add these two masses up using this equation here, and the result is the atomic weight of chlorine that exists in natural abundance. This is what is shown on the periodic table. So, let's look at this. So here is lead, for example. This is lead, so look at your periodic table, get your periodic table and try to find lead here. You will see that there's an 82. That is the atomic mass, or the number of protons and electrons. Here is the atomic weight, which represents here the isotopes that exist in nature, the average mass. Okay, so we have here, so let's consider one of these isotopes. It's lead 208. So if you consider one of these isotopes, which contributes to the overall atomic mass here, it has 82 protons and 82 electrons. So that's why here it is 208, because it has 82 electrons, and the difference would be 126, which would be neutrons. So the difference between the number of protons and the actual number of neutrons and protons would be the number of neutrons. Let me say that again. The difference between the number of protons and its atomic mass would be the number of neutrons. These are just some other descriptions of the atom, show you that it's very light, and of course its density is very, very small. But the take-home lesson here is that the atomic weight has the different isotopes. If you should look at one isotope, for example, you should be able to determine the number of neutrons if given the actual atomic mass for that isotope. Let's see if we can apply this. knowledge here. Which subatomic particle or particles are found in the nucleus? So again, you need to visualize here the nucleus. Remember, a sphere represents the atom, and within the center of that sphere is a nucleus which has the protons and electrons. And outside of that sphere, you have the electrons. So let's look at the choices. Subatomic means within the atom and in the nucleus. Is it electrons? We have defined already that the electrons are outside of the nucleus, so that may not be a choice. Neutrons, possible. Protons, yeah, possible. But here's another choice that's interesting. Neutrons and protons. So you'll have to think of these carefully and make the best choice. The best choice here, as you can imagine, is this, based on your knowledge of the definition. Okay, let us go on. Let us apply this concept here in terms of having an new element, an element that has two isotopes. So there are the two isotopes of this element here, quininium, and it has 40.3% of this isotope is 296.78 AMUs. That is the weight. So it has two isotopes. Here's one isotope, and here's the other isotope. The mass of this isotope here is 296.38, and its percentage in nature, its natural abundance, is 40.3. The other isotope is 301, and its percentage in nature is 59.7, and its mass is 300.88. The question now is, what is the atomic weight of this new element? Okay, notice again it says here to the correct decimal places. So we are applying quite a few concepts. Make sure you remember how to report numbers to the least precise measurement. Okay, so what you'll have to do here is to use that equation that we used for chlorine. So you may want to pause the video here and go back to that equation we used to determine the atomic weight of chlorine, which was the sum of the isotopes that contribute to the atomic weight. So in this case, you take 40.3 divided by 100 times 296.78 plus the other isotope, 59.7 divided by 100 because it's percentage, times the weight, which is 300.88. Plug those numbers into your calculator and see what you get. Okay, so you can pause the video here and do that calculation before you see the answer on the next slide. The answer is, or the best answer is, this one. Notice this here is essentially the same number, but because the least precise is 2 decimal places, you cannot use 4 decimal places as your answer. So you'd have to report it to 2 decimal places as shown here. Okay, again, do your calculations. You will see that these numbers here are in the range, but not precise. Okay, so once again, you should be able to apply this concept as we go through this chapter. And this is the end of this lecture. So continue reading. The next lecture we'll post is that on the electronic structures. Where are these electrons in the atom? So continue reading your material, and I'll post the next video during the week. So all the best in reading, and continue to study hard. Okay? Bye.